Today, let's try to work out one of the problems in Norman Nice's book, Control Systems book, the 7th edition. This is problem 2.42. What we've got is a disk. We've got a mass with a spring, and the mass is being pulled with a force. One of the things that we've got in here, sometimes we'll put a little bit of damping. There's some kind of a fluid damping in here. I'm going to call this FV1 and FV2. So the way we're going to start this thing out, we're going to look at, first we'll do a free body diagram of the disk. Let's do a free body diagram of the disk. And so we'll draw, what we're going to do is draw all of the forces on the disk. We've got to maybe establish some datums first. I guess I'm going to establish some datums this way. So I'm going to make a positive x direction be in the same direction as the positive force. And then what we can see is if when the mass moves in a positive x direction, then the disk will move in this positive theta direction. And so we're looking at this as, again, this is positive theta. And so before we forget to do anything else, we'll just put this D'Alembert inertial force, J theta double dot, in a direction opposite. Now, we can see that there's a damping force somewhere between these two, the disk and the mass. And so what I'm going to do is it's true I cheated and I know what direction to put this force in, FV1. However, it doesn't really matter. The minus sign will float its way out as long as you're careful about it later somewhere. And so FV1 is a viscous damping force, vicious damping. Oh, okay, it's not vicious. It's viscous damping force. It's a viscous damping force, and it's equal to B. So we certainly know that if we move this mass in a positive direction, it's going to make this force. So that's x dot. And the thing about it is it's going to be reduced by the amount of motion that is going on in this disk. So if both of those points are moving at exactly the same direction, then r theta dot, then that force would be 0. And so we can write the equation of motion for this. I'm just trying to see what I'm going to do. Let me write this equation of motion number 1 up here. I'll just write it. Uh-oh, I'm falling off the page. Oh, I thought I had that all worked out. Okay. The equation of motion number 1 is going to be J theta double dot minus, I can do it this way, minus or plus J theta double dot minus R times FV1 is equal to 0. And if I plug in everything I need for that, then it's going to be J theta double dot minus R. FV1 is B times x dot minus R theta dot equals 0. Of course, there's a little bit of algebraic stuff that we can do here. Minus plus R squared B theta dot is equal to R B x dot. And one of the things that we see here is that well, let's go on. We're going to draw a free body diagram now. Let me see if I've got enough space at the bottom of this page here. I'm going to move it up just ever so slightly. I'm going to draw a free body diagram of the mass here. Again, before I forget, I'm going to put the D'Alembert inertial force on here, mx double dot. I don't even have to mess with this force here. This is FV1. Now, I will say that on the bottom of this thing, there's another force. It's a FV2 is a inertia, vicious damping force that is going to be B. I'm going to use the same, I'm going to say it's the same coefficient of damping just to make it easier. This is going to be B times X dot is going in that direction. Then we also know that if I stretch this spring out, if I move this in a positive X direction, that spring force is going to be K times X. And then finally, we'll just put the last piece on here, which is F. And now we've got the free body diagram of the block. This is the equation of motion number 2 is going to be, so we're going to sum up mx double dot plus bx dot plus fv1 plus kx is equal to F. And so here's our 2 equations of motion that we have. This one's a little less clear. Oftentimes I make a big deal out of this, but you know, in this one of the things that we see is that this damping force is a linear force. It's in the linear space. And in this equation, we've reflected that damping force into the rotational space. And the way forces go, dynamic forces move by the gear ratio squared. In this case, the ratio between x and theta is r, and that's why you get an r squared in here. So we can actually write this one again, mx double dot plus bx dot plus fv1. We've got fv1 in here. This is going to be b times x dot minus r theta dot plus kx equals F. All right, so we have our second equation of motion here. Now, we'll notice that we can't relate, because this is a viscous damping coupling. These are 2 equations. They're called coupled equations because in the first equation, the equation for the first variable has the second variable in it. And the equation for the second variable has the first variable in it. You know, I shouldn't have put this box around here. I should have done a little bit more algebra is what I should have done. So this is mx double dot plus 2b x dot plus kx equals F plus b r theta dot is how I should have done it. So I really should have put this should be our second equation of motion, 1 and 2. Forget that. Just pretend like I didn't do that. I won't scratch it all out, but there you go. Now, one of the great things about Laplace transforms is that we can just take the Laplace transform of this equation simply and easily. ms squared plus 2bs plus k times x is equal to F plus b r s theta. So now we have the equation, this equation, and actually what we can do is we can solve this equation for x. What Laplace transforms do is they convert differential equations into algebraic equations. And so x is equal to F plus b r s theta divided by ms squared plus 2bs plus k. So now we have an expression for x that we can plug in to equation 1. Well, let's take the Laplace transform first. Laplace transform it, and then what we'll have here is j s squared theta plus b r squared theta s is equal to r b s x. And of course we can just plug in for r b s x, so I'm going to put equal sign. This is F plus b r s theta over ms squared plus 2b s plus k.
Okay, you may notice that there's a difference in video here, and that's because I made a mistake on the first set of analysis. You saw that oops there. And I'm going to read, this is a Norman Nice problem 2.42. And I'm going to just rewrite this equation. So this is a JS squared theta plus BR squared theta S is equal to, so this, I left this off, RBS times F plus RBS theta over MS squared plus to be or not to be S plus K. That's X. So the way this is going to work is that I just have to cross multiply. So I have to say JS squared theta plus BR squared theta. Yes. S times MS squared plus B 2B S plus K is equal to R B S F plus R B S theta. Okay, so we just have to cross multiply it. I have a method that I use. I always do JS squared theta times MS squared plus J times 2B S cubed theta plus J K S squared. So I do first times that one. And then I'm going to do just basically the MBR squared theta S cubed plus, so this times this times this is going to be BR squared. There's two of those. There's two B's squared, so it's B squared, 2B squared R squared theta S squared plus BR squared theta S K. So that's all of those is equal to, so whatever's on this side is going to be equal to R B S F plus R squared B squared theta S squared. Whew. Okay, right? So we'll just add these together and we'll get this. So this is JMS squared plus 2JB plus MBR squared S cubed plus JK plus 2B squared R squared S squared plus B R squared theta, oh, no theta, KS is equal to RBSF. And if it's okay with you, I'm going to take this one and I'm going to move it over onto this side. So this is a minus B squared R squared on that side, right? Oh, all I have to do to make that work right is that I have to definitely multiply that whole thing by theta. Okay? And so now what we could do is we could just form the transfer function T of S for this system. The transfer function is the output over the input, which is going to be theta over F. And we can write these all in. So this is RBS divided by JMS. So you'll see here, this is S squared and S squared. That was supposed to be a fourth. S to the fourth plus 2JB plus MBR squared, MBR squared, S3 plus JK plus 2B squared R squared, S squared. Oh, not two of them, because 2 minus 1 is 1, plus b squared, no squared, b r squared ks. There's my transfer function. Now, just so you can see it, look here. Looky here. Let's make that a 3, 2, 1, 0. Okay? So here's our transfer function. Now, if I wanted to see how this transfer function works, I'm just going to use my MATLAB code here. I'm going to use a different code. So in MATLAB, I'm just going to say, oh, well, TS is equal to transfer function. And I can put in what is in the numerator, which is RB. And I can put in, comma, what's in the denominator, which is going to be, is it okay if I just do it this way? 1, 2, 3, 4. These 4 coefficients. And here's why I'm going to do it that way, because I'll put a little arrow. That goes there. This goes here. This goes here. And this goes here. And here's why I'm doing it that way, because I just said, okay, so once you get into the transfer function, you're not doing things symbolically anymore. So we're going to just say that I'm just going to let J equals M equals B equals K. All of those things equals 1. This isn't a very good equation because I'm equating things that have different units. That's actually, you'll see I made a mistake on the other one. I'm not sure how much of that I'm going to show you because it's kind of a waste of your time to show you video of me making a mistake in algebra. And so what I can do is that this is going to tell me that TS, this is what MATLAB is going to give me back. It says, oh yeah, TS is equal to 1 over s cubed plus, so that's 3, 2 times 1 times 1 is 2, plus 1 is 3, s squared plus 1, 2, s plus 1. So it's going to tell you that. And then you issue the next command to MATLAB. You just say, hey, I'd like to see what a step of TS looks like. So when I made a mistake, I did this. I didn't know if this was right or wrong, but you'll see in a later video that I did this a different way and found out why it was right or wrong.
So we've gone through the whole problem and gotten a transfer function out of it. What I'd like to do now is start back at our 2 equations of motion, the 2 equations of motion that we have, and we should learn how to use Simulink to solve these 2 equations of motion. There's times, so Simulink and block diagrams are mostly the same. So part of this is this is good for us to learn how to do some block diagram algebra, and it's also a good time for us to learn how to do Simulink. So I'm just going to write these 2 equations again. Sorry, J theta double dot plus R squared B theta dot is equal to R B X dot. And then the second one is going to be mx double dot plus 2b x dot plus kx is equal to f plus b r theta dot. So the rule when we're doing block diagrams is we kind of want to start at the beginning. I would sing you that song from Sound of Music. Start at the very beginning, a very good place to start, oh, dear. Ask me to sing the other part of that song another time, but here we go. So what I'm going to do, since I'm going to assume that f is the input, that means that's kind of where things start. What I'm going to do is I'm going to solve this equation. This is kind of the beginning equation. I'm going to solve it for its highest derivative. Mx double dot is equal to f plus br theta dot minus 2b x dot minus kx. So I'm going to solve it for the highest derivative. Solve for the highest derivative. Now in Maine, this means something else, the highest derivative, right? Maine and Colorado, I guess. So there's other places now, but. And then what we're going to do is we're just going to, we actually do this for both. We're going to actually do this for both of them. So let's just go ahead and do this one too. This is going to be J theta double dot is equal to RB x dot minus R squared B theta dot. So let's see. If we're going to do block diagrams, we're going to have F coming in here. So F comes in. We got F. We have to add plus. What we're going to do is we're going to, I've kind of, again, a lot of times these things are scribbles, these block diagrams, and if you do them once, you'll kind of see how to do it another time. So what I want to do in here is I'd like to bring in AB R theta dot. I'd like to bring that in here so that it takes care of that one. Then I'm going to subtract off here a 2b x dot. And I'd also like to subtract off here, that's a minus sign, I'd like to subtract off here minus sign ak times x. So if I do this block diagram algebra here, this is more or less the summing junction for equation 1. Sometimes I even do this a little bit. Sometimes I'll put a little dotted line around this, because this summing junction represents equation 1. If I do that, you know, what I get out of that is, of course, mx double dot. And do I want mx double dot? No, I don't want mx double dot. So let's start picking away at that. We're going to do a 1 over m. That's going to give me x double dot. I don't even want x double dot. And the good news is, because I know something about Laplace transforms, I know that if I multiply this by a 1 over s, I get x dot out of it. I'm going to do that again, and that's going to give me x. Now, I'm going to look at my second equation, and I'm going to see that I need to get an rbx dot. So here, I'm going to take this guy right here. I'm going to pull it out, and I'm going to multiply by rb. And that's going to give me rbx dot. And if I take that and I subtract off of it this r squared b theta dot, if I subtract off that, then I get j theta double dot. But I'm not interested in j theta double dot. 1 over j, that is theta double dot. I'm not interested in that. 1 over s, that is theta dot. And I'm not interested in that. 1 over s, that is theta. So I can now close these gaps that I've left here. Here's RB. Sorry if I'm getting a little bit small. I'm going to draw this again, but it'll be fine. Here is a k times x. Excuse me. Here is a 2b times x dot, and then here is a b r theta dot. So here's a perfectly good block diagram. That's a perfectly good block diagram. We can implement this in Simulink, and we will implement it in Simulink. The one thing, again, that I'm going to remind you, all of you electrical engineers, is I call it block diagrams. In Simulink, all of these gains, as it were, they will look like triangles. So just be aware of that. They will look like triangles, and then that'll make it look. Let me just go ahead and just do a little bit of manipulation on this block diagram to make it look a little bit more like an input-output kind of thing. So what I'm going to do here is I'm going to just go ahead and I'm gonna trace this through. I'm gonna go through this first. This is 1 over m. This is still x double dot. 1 over s. This is x dot. Now, in this case, I'm not going to mess with, I'm just going to do an RB. That's plus. This is a j theta double dot. 1 over j theta double dot. 1 over s theta dot. 1 over s theta. Ta-da. Now, we still have to put in all the other stuff. Well, let's start with the easiest stuff here. So we can certainly just do this as r times b. That's a minus sign. I'm going to follow this one around. So I have x dot coming through here. This is kind of where it might get a little bit weird. I'm going to put this back this way. Here's a 1 over s coming this way. And then I'll multiply it by k. Minus, I should keep my minuses and pluses straightened out. So, right, this is 1 over s. So I've still maintained this line of information flow, x dot. So I'm going to also do this one. This is going to be 2b. So this is still 2b x dot. And this is still kx. There's a minus sign there. This is r squared. Oop, I left out my r squared here in both of these cases. R squared b theta dot. That's still r squared b theta dot. And this is still r b x dot. So earlier I mentioned that this is the summing junction for equation 1. And sometimes I'll put this dot around here too, just so that we can know that this is the summing junction for equation 2. So I kind of maybe keep kind of that straight a little bit. We've got one more piece of information here that we have to deal with, and that is to take this RB, and I'm going to point out to you that this is a plus sign here. So we should just be able to put this into Simulink and simulate it, and it should give us exactly the same answer that our step response gave us the other way. So one of the reasons that I'm showing you this is that, you want to have more than one way to try to attack a problem so that you can convince yourself that it is correct.
Well, let's try. We're going to type the word Simulink. We'll have to wait for a few minutes, a few seconds here. It takes a while for Simulink to load up. What comes up is the library browser. So it's got different blocks, and we're going to open the new file. We're going to have a new model. When we open up a new model, that opens up a window within which we'll put our block diagrams that are the Simulink model. So I'm going to move this library somewhere where I can also see it here. So we need to put in some pieces. A lot of times I just use the commonly used blocks. Continuous, no. I never can find anything in here. Oh, commonly used blocks. Frequently used. There we go. So we definitely need a gain. We're going to need a gain. We're going to need an integrator. We know that. And we're going to need a summing junction. We know that. So mostly those are the blocks that you use all the time. That's what you need. You can always do Control-C, Control-V to copy, paste the blocks. I'm going to start arranging these into the same form that we have on our sketch of the block diagram, right? So, we'll need a signal generator. We'll need an input of some sort. I like to use a signal generator. You can also just double click and change the names of these blocks. I'm going to call this F because F is our input. So these summing junctions, you can just put as many of these things as you want. So I'm going to do plus, plus, minus, minus. That first thing is a pipe sign, and that arranges the order. This, I just got lucky here, and that's plus, plus, minus, minus. There's a cottage industry on how to arrange those pluses and minuses in here. I'm going to change this gain to the 1 over m. That'll be our first block. And I'll just leave these names of these integrators as integrators. So here's integrator 1. I'll need 2 integrators in a row. I Control-C, Control-V to copy that gain. I'm going to call that RB.
Yeah, you want to get that one.
R times B. You can call it whatever you want. It's just helpful to, I need another summing junction here too. It's helpful to label these things. This summing junction, I don't need these extra things. In fact, what I need on this summing junction is a plus minus. Right, so they kind of scale all this stuff for you. Need a couple integrators. Let's get a couple more integrators here. Control-C, Control-V. We're all done. That's most of what we definitely need another one of those blocks. So let's copy that. And then you can right click on this, and that gives you the option for rotating and flipping the block. I'm going to flip it so that it goes the right way. That way I've got a block going the right way. So I definitely also need an output device. So I'm going to use a scope as my output device. What I haven't shown in here is how to put values in here. You can just double click on these to put values. The default is 1, and if you remember, I named all my gains 1, so I don't have to do very much with it. So you can also just drag, from one to the next, but you can, if you highlight one and then click Control something, there's a trick. Eventually MATLAB will tell you, like, hey, there's a trick to doing this. So this, Control Enter or something, I forget what. So you can do it quickly. I like to arrange my stuff pretty nicely. It helps in the end to arrange that stuff pretty nicely. Right, okay, so now we've got that loop taken care of. I like to line this stuff up. Here I'm going to add these loops that occurred on the in that first equation. I'm going to add those loops too. Oops. Let me change names of this stuff. Again, it's better to keep your names descriptive. We'll put that one on this side. I've done this a time or two, so I kind of know a little bit better what. Or what arrangements in this stuff look best. Of course, we have a sketch to go by too, and here we go. We pretty much have our sketch and our Simulink diagram equal to one another. That one, I needed to make that a value of 2 if you look back at C. 2 times B is 2. I think that's the only one I have to change. Save as. I'm going to save this file and I'll provide it to you. This stuff needs to be dry. Huh, wonder where I am. I might cut some of this out.
Hi.
Norman, problem 2.42. Now we'll just run it. We can double click on the scope to see what the output looks like. Huh. Sine wave. Oh yeah, that's right. Because I'm looking at steps, and there are step inputs in here. I usually, you start with a step. So I'm going to use a square wave, and I'm going to make this frequency really slow so it'll make it look like a step input. If I wait long enough, it'll look like a square wave. Then I'm going to run that again. I'm going to double click on the scope. It went down, and that's another like idiosyncrasy that you have to kind of get used to. If you use the scope to make a square wave, the amplitude should have to be -1 so that it goes up to begin with. Also, it's worth your effort to right click on the scope, open it up, and go to the tools settings. So first of all, the history, they have this thing limit to 5,000 data points, and it might not happen at first, but eventually you will not get all your data. So I usually say, like, I don't want to do that, and I want to save it to the workspace. And I might want to save it to the workspace with my own name, so I'm going to call it theta. And then I would like to make that be an array. I'm not a computer scientist enough to know how to do structures. I can do kind of, but yeah, it's better not to do it that way. Now we'll run it again. We'll double click. So sure enough, that's our response. But we might want to go through and check to see that our response, I don't know what I'm looking for here. Oh, I was worried a little bit. It looks like there's like a little bit of a delay at the beginning, but I don't know for sure. I can't tell exactly on this thing. I should have, there's an expanding, you can zoom in. But I didn't do this. Save. I'm going to save that. Now I'm going to go back to my MATLAB.
How are you?
And show you how to import that data. So that data is already in the MATLAB window. You can see whose. You can see theta is a 2-element vector, and T out is the time. Oh, I guess it's T out. I don't even have to do what I'm doing here. Maybe I do. So I know that I know from experience that the first element of theta is time vector, and the second element is what I'm displaying in my scope. So I can just plot those two things. So, is that right? Probably. And if I want to check, guess what I can do if I want to check? Oh, I should just go back and use the analysis that we did the first time. TS equals transfer function. It wants numerator and denominator form. We know that numerator is 1. That's only because RB equals 1. And that's the, if you go back and look at the notes, that's the denominator transfer function. So here's a continuous time transfer function. I was going to open up a new figure to put, and then I decided, no, we should we should put them both on the same plot. So I'm going to type hold on, and then I'm going to type this step, TS. Now I'm going to go look at that figure again. Oh, wow, step TS. I think it has to load a bunch of stuff. Hey, that looks the same. Oh well, usually what I do is, if I'm comparing stuff, I try and make it like I make that red. I want a red line. And then I see, oh yeah, okay. So they were the same. So that gives me some hope that I've done some of my work correctly, because they're both the same. Sometimes I zoom way in. Yeah, there's lines. There's 2 lines there, so I just want to make sure. Okay? And so now we can see how to use Simulink.